In this video, we will be looking at the topic Total Probability Theorem. Before diving into the theorem, let us first solve and understand the given example. Given is a shelf with 4 compartments. Compartment 1 has 1 yellow coin and 1 green coin. Compartment 2 has 1 yellow and 2 green coins. Compartment 3 has 1 yellow, 2 green and 2 red coins. Compartment 4 has 1 yellow, 2 green, 2 red and 2 blue coins. Now, a coin is chosen at random from any one of the compartments. What is the probability of the chosen coin being a yellow coin? To solve this particular question, we will be using the total probability theorem. Since there are 4 compartments, there are 4 ways in which a yellow coin can be chosen. Let E represent choosing a compartment and let A represent drawing a yellow coin. We shall look at these ways as 4 different cases. Case 1. Consider compartment 1. Let E1 represent selecting compartment 1 and let A represent choosing a yellow coin. The probability of choosing compartment 1 out of the 4 compartments, that is, P of E1 is equal to 1 by 4. We know that compartment 1 has 1 yellow and 1 green coin. That is a total of 2 coins. The probability of choosing a yellow coin out of the 2 coins in compartment 1 is given by P of A given E1, which is equal to 1 by 2. Here, the numerator 1 represents the number of yellow coins in the compartment and the denominator 2 represents the total number of coins in the compartment. Now, let us look at case 2. The probability of choosing compartment 2 out of the 4 compartments, that is, P of E2 is equal to 1 by 4, where E2 represents choosing compartment 2. We know that compartment 2 has 1 yellow and 2 green coins, hence a total of 3 coins. The probability of choosing a yellow coin from the 3 coins present in compartment 2 is given by P of A given E2. Here, A represents choosing a yellow coin. P of A given E2 is equal to 1 by 3, where 1 represents the number of yellow coins in compartment 2 and the denominator 3 represents the total number of coins in compartment 2. Case 3. Similar to the first 2 cases, the probability of choosing compartment 3 out of the 4 compartments is represented as P of E3, where E3 means choosing compartment 3. P of E3 is equal to 1 by 4. We can see that compartment 3 has 1 yellow, 2 green and 2 red coins, making a total of 5 coins. The probability of choosing a yellow coin out of the 5 coins present in compartment 3 can be represented as P of A given E3. This is equal to 1 by 5, where the numerator 1 shows the number of yellow coins in compartment 3 and the denominator 5 shows the total number of coins in compartment 3. Let us now look at the final case, case 4. The probability of choosing the 4th compartment, P of E4, is equal to 1 by 4, where E4 represents choosing compartment 4. It is given that compartment 4 has 1 yellow, 2 green, 2 red and 2 blue coins, making a total of 7 coins. The probability of choosing a yellow coin from the 7 coins can be written as P of A given E4. This is equal to 1 by 7, where the numerator 1 shows the number of yellow coins in compartment 4 and the denominator 7 shows the total number of coins in compartment 4. Now we have one step left to obtain our final solution. The question has asked us to find the probability of choosing a yellow coin from the entire shelf. We must combine the answers of all our cases to find the same. Let A represent choosing a yellow coin. Probability of choosing a yellow coin from the entire shelf will be given by P of A. P of A is equal to the summation of the product of probability of choosing the compartment and the probability of choosing a yellow coin in the compartment. Or P of A is equal to the probability of choosing compartment 1 into the probability of choosing a yellow coin in compartment 1 plus probability of choosing compartment 2 into probability of choosing a yellow coin in compartment 2 plus probability of choosing compartment 3 into probability of choosing a yellow coin in compartment 3 plus probability of choosing compartment 4 into probability of choosing a yellow coin from compartment 4. Solving the 4 cases, we already have found the values for the same. Now, we shall be substituting the values. P of A is equal to 1 by 4 into 1 by 2 plus 1 by 4 into 1 by 3 plus 1 by 4 into 1 by 5 plus 1 by 4 into 1 by 7. By simplifying further, we arrive at the answer 247 by 840, which is approximately equal to 0.3. And hence, that is our solution. Result: the probability of choosing a gold coin from the entire shelf is equal to 0.3 or 247 by 840. Let us proceed to understand the law of total probability. Let S be the sample space and let E1, E2, E3 and so on till En be n mutually exclusive and exhaustive events associated with a random experiment. Now, we shall understand this sentence with respect to our previous example. Here S or sample space means the space which contains all of the events or the elements. In our previous example, the shelf or the cupboard was the sample space as it contained all of the compartments and the coins. Next, E1, E2, E3 and so on till En are said to be n events. In our previous example, choosing a compartment represented these events. Now we have two new terms here, mutually exclusive and exhaustive. Let us look at them individually. Mutually exclusive events. A set of events where no two incidents can occur together are called mutually exclusive events. In our previous example, when we chose compartment 1, we could not choose compartment 2 at the same time. Or when we chose compartment 3, we could not choose compartment 1 at the same time. In simpler words, when we choose one compartment, we cannot choose any other compartment simultaneously. Such events are called mutually exclusive because, as the word suggests, two events cannot occur simultaneously. Let us look at exhaustive events. When accumulation of all the events gives us the sample space, the events are called exhaustive events. In our previous example, the 4 compartments were our 4 events. All the 4 compartments put together gave us the shelf or the cupboard, which was our sample space. Therefore, these compartments or these events are called exhaustive events. Now, let us look at the next statement. If A is any event which occurs with E1, E2, E3, and so on till En, then P of A is as follows. Now let us again compare this statement with our previous example. Here, let us consider A to be choosing a gold coin, E1, E2, E3, and so on to be choosing compartment 1, 2, 3, 4 respectively. Then P of A, a probability of choosing a gold coin, will be equal to probability of choosing compartment 1 into probability of choosing a gold coin in compartment 1 plus probability of choosing compartment 2 into probability of choosing a gold coin in compartment 2, and so on. Since there are n events here, the formula can be written as follows. P of A is equal to P of E1 into P of A given E1 plus P of E2 into P of A given E2, and so on until P of En into P of A given En. To understand the theorem better, let us solve another question. A bag contains 4 white and 5 black balls. Another bag contains 6 white and 7 black balls. A ball is transferred from first bag to the second bag, and then a ball is drawn at random from the second bag. Find the probability that the ball drawn is white. Here, we shall be looking at this in 2 different ways. Because a white ball can be drawn from the second bag in 2 mutually exclusive ways. The first way is by transferring a white ball from the first bag to the second bag and then drawing a white ball from the second bag. The second way is to transfer a black ball from the first bag to the second bag and then draw a white ball from the second bag. Now let us look at case 1. Here we will be transferring a white ball from bag 1 to bag 2. Let E1 represent a white ball transferred from first bag to the second bag. Probability of E1 is equal to 4 by 9, as there are 4 white balls in bag 1 and a total of 9 balls. If E1 has already occurred, that is, a white ball has already been transferred from first bag to the second bag, then the second bag contains 7 white and 7 black balls. So, P of A given E1 will be equal to 7 by 14, where A represents a white ball drawn from the second bag. 7 here in the numerator represents the number of white balls in the second bag, and 14 in the denominator represents the total number of balls in the second bag. Now, let us take a look at case 2. In case 2, a black ball is being transferred from the first bag to the second bag, and then a white ball is drawn from the second bag. Let E2 represent a black ball transferred from the first bag to the second bag, and let A represent a white ball drawn from the second bag. P of E2, or probability of a black ball being transferred, is equal to 5 by 9, as the first bag contains 5 black balls and 9 balls in total. If E2 has already occurred, that is, a black ball has been transferred from first bag to the second bag, then the second bag contains 6 white and 8 black balls. So, P of A given E2 is equal to 6 by 14, where the numerator represents the number of white balls and the denominator represents the total number of balls in bag 2. Using the law of total probability, we obtain P of getting a white ball, that is, P of A is equal to P of E1 into P of A given E1 plus P of E2 into P of A given E2. This is equal to 4 by 9 into 7 by 14 plus 5 by 9 into 6 by 14. This is equal to 58 by 126. Or when further simplified, it is equal to 29 by 63. Therefore, the probability of a white ball being drawn from the second bag when one ball is transferred from the first bag to the second bag is equal to 29 by 63.